and we are going to take notes from one of my videos on a separate sheet of paper, and you will upload a picture of that paper to Canvas. All right, let's go ahead and begin. Okay, here we go. All right, let's start with the whole culprit to this problem that we're having with ocean acidification, which is excess CO2. And it's mostly due to these factories from industrialization that harvested the fossil fuels and are burning them and releasing the CO2 into the atmosphere. So whenever you burn something that used to be alive, you get carbon dioxide as a byproduct. Okay? Before industrialization, our oceans and trees were doing a pretty good job absorbing our CO2 outputs. But now we're overwhelming the system, and all of this CO2, actually 50% of it, is going to be absorbed into the great carbon sink called the ocean. So let's go through this reaction. CO2, carbon dioxide, is going to combine with water to form an unstable carbonic acid. So if I put these atoms together, the carbon and 2 oxygens and the H2O, I get 2 hydrogens and a CO3. Okay, it's balanced. This is called carbonic acid. So we see the word acid there. That's going to lead to the acidification, but we'll add another layer to that. It's not exactly this that's causing acidification. And then this breaks down further to bicarbonate. So it's going to lose 1 hydrogen. So kick off 1 hydrogen out of that equation. And now it becomes HCO3. This is going to be bicarbonate, which is not super acidic. In fact, it's kind of what you see when you have baking soda at home. It's an acid reducer. So it's going to naturally kind of go back and forth between these two forms. But because of excess CO2, we are accumulating this hydrogen, and that is the definition of an acid, having a lot of hydrogen ions in solution. Okay, so this hydrogen is going to take one of 2 roads. All right. It's going to either stay single, okay, and just accumulate. It's supposed to be an H+. So it's going to stay single, and by that I mean it's not going to chemical bond with anything. It's going to stay single. And as a result, those excess hydrogen ions are going to acidify the ocean. Okay, guys, you might be annoyed, but this analogy is just going to keep going. It's going to stay single, or it's going to steal someone else's carbonate. So it's going to stay single, or it's going to get in a relationship with someone else's significant other. All right, that significant other is carbonate. Okay, so you guys, what relies on carbonate in the ocean are things called the calcifiers. So let's just take a little sidebar and make a list of the things that rely on carbonate. So these are going to be your calcifiers. And these are going to form shells with calcium carbonate. That's going to be Ca, capital C, lowercase a for calcium carbonate, CO3. The calcifiers. All right. So, what are some calcifier examples? Anything with a hard shell. Let me show you guys some pictures while you're writing. This is a calcifier. It's got a hard shell. You can tell it's an abalone because it has these holes right there on the outside of its shell. So I like to tap it on the desk so you can hear it. That's calcium carbonate, which you guys, we know calcium carbonate a lot as chalk, but it's a little harder than that in the ocean. Here you have a full clamshell, calcium based. Here you have your beautiful sand dollar without any spine, calcium based. Here's one you might not recognize. This is called a nautilus. This is a cousin to an octopus and a squid, and its whole fleshy body is inside, and it's got its little feet hanging out like that. Okay? That shell is calcium based. You also have the sea urchin test, or the shell. I don't know if you guys can see this, but it's a cousin to the sea star. The sea star has its star shape flat. But a sea urchin wraps its feet in on itself like this. So you can kind of see foot 1, 2, 3, 4, 5 right there. It folded in on itself like a bail ball or a bail bun. Okay, calcium base. And last one I'll show you is this coral skeleton. You guys can see if you look really close inside of those holes, that's where the fleshy coral polyp lives, the actual animal. But this is the shell of the coral. All right, so these are going to be your calcifiers. These are going to rely on a very important substance that hydrogen is going to compete with it for. All right, so you're going to have your coral, all of your seashells, and some other animals like the nautilus, but we don't need to focus on that now. Speaking of focus. Okay. So in order to build their shells, they need carbonate and they need calcium. They need to bring those two together. So let's go ahead and sketch a seashell or whatever one of these you want to draw. All right. So this is my shell. What could be my coral? And it is constantly growing. In order to grow, you have to build new shell. So it's constantly taking calcium out of the water and carbonate out of the water and forming its shell with CaCO3. So it's always doing this. It's taking in calcium, it's taking in another carbonate, and it's forming its shell. It's constantly building. All right. Well, hydrogen is going to come in and start stealing the carbonate from the shelled creatures. That's going to cause a problem. So this hydrogen right here is going to steal the carbonate, and it's going to form bicarbonate some more. So this is going to steal the carbonate. It's supposed to be that. From the calcifiers. So now you guys, all of the sudden, we are starting to see these shelled animals lose their shell, like slowly get weaker and weaker and weaker. Okay, this is going to be a problem. They're going to die. They're going to be more defenseless. They're not going to have enough energy to be reproduced. So we're going to see a decrease in the health of the shelled animals and the coral reefs. More on that later. So this pesky hydrogen is either going to raise the acidity of the ocean by releasing hydrogen ions, or it's going to steal the carbonate needed to build calcium carbonate shells. So it's going to steal calcium's partner and it's going to combine with it to form bicarbonate instead of allowing it to make the calcium carbonate that's necessary for shell building. So this is how ocean acidification happens. CO2 enters the water, it forms carbonic acid, that carbonic acid dissociates into these hydrogen ions and so on.